Today, Kugan will be speaking about what you should and should not do in your programs, and what is undefined behavior, and how compiler optimizations can get you when you use non-standard or non-conforming code in your C, C++, or other programs. Kugan is an engineer at Linaro's toolchain working group and is working primarily on GC optimizations.
Thank you, Maxim. So thank you all for coming for this presentation. In this presentation, I'm going to be talking about, as Maxim said, what is undefined behavior and why we all should care about it. To begin with, I'll start off with the definition of undefined behavior. Then I'll give you a few examples which we extracted from various bug databases, including GCC. Then I'll talk about ways in which we can detect undefined behavior, but please keep in mind there is no foolproof way of detecting all the undefined behaviors. And you've got to be careful when you write as well as when you review your application. With that, I'll conclude this presentation. Okay, let's start off with an example. How many times do you think this loop in this piece of code would iterate? Anyone want to make a guess?
And we have candies for the right answers.
Sorry? Okay, let's assume that the D is properly initialized and there are values in that one. Yeah.
Please raise your hand so that we can get you a mic.
Okay. I think some of us would have seen this earlier, so anyway, I'll just move on. And that particular piece of code actually was trying to read the values in array D, which has 16 elements in a loop, one by one, and trying to add the absolute value. And it was working as the user intended with various versions of GCC, but when we moved to GCC 4.8, this turned into an infinite loop. So, like if you are interested in more information about this bug or whatever it is, you can actually refer to the GCC bug database. But let's look at the standard. The C standard says it is legal for a pointer to point to one element past the end of an array. But accessing that element is undefined behavior. So keeping that in mind, if you look at the loop again, the place where the loop counter k is incremented, we are doing a pre-increment of k and accessing D, array D with that element. Therefore, if the k is 15 or beyond that value, we are actually invoking undefined behavior according to the standard. So therefore, the condition k less than 16 is always going to be true for a correct program, which doesn't invoke undefined behavior. So GCC saw this one and optimized away the condition as always true. That resulted in infinite loop. In fact, if you compile this piece of code with current version of GCC, it will in fact give you a warning saying that iteration 15 invokes undefined behavior. Now that we looked at an example of undefined behavior, let's look at the definition of undefined behavior. It's, according to the ISO standard, it's behavior upon use of non-portable or erroneous program construct or erroneous data for which this standard imposes no requirements. And CFAQ definition is even more clear. It says anything at all can happen. The standard imposes no requirement. The program may fail to compile or it may execute incorrectly, either crashing or silently generating incorrect result. Or it may do exactly what the programmer intended. That's exactly what was happening with the example we looked at. It was working, but that didn't mean that it didn't have undefined behavior. The undefined behavior can lead to very subtle bugs or have critical impact on security, so it must be avoided. Standard also defines other kinds of behavior other than undefined behavior. There is implementation defined behavior that's defined as unspecified behavior, where each implementation documents how the choice is made. A good example for this one would be the size of integer. And the other one is unspecified behavior. Use of an unspecified value or other behavior where the international standard provides two or more possibility and imposes no further requirements on which is chosen in any instance. A good example for this one again would be the order of evaluation of arguments in a function. Whether you do it from left to right or right to left is an unspecified behavior. A particular implementation of a compiler can choose anything between one of them and can document it. There is also a local specific behavior, which is not that interesting, but it basically says that depends on local conventions or nationality, culture, and language that each implementation documents. Now that we looked at the definition of undefined behavior, let's see why the language specification leaves some of the behavior as undefined. C and C++ is designed to be an efficient low-level programming language, which offers compiler writers freedom to optimize, because the users of C and C++ program most often care about performance to the last extent. Unlike safe languages like Java, which have very few undefined behavior, but safe and reproducible behavior across implementation comes at the expense of performance. So if you look at this very simple example, x multiplied by 2 divided by 2, this can be optimized to x only if we assume that x multiplied by 2 doesn't overflow. And if we take this simple example and compile with GCC, it will in fact generate what you see on the right. This is the optimized Jimple. So it is actually assuming that it's going to be x. Whereas if you compile the same application with frapv, saying that operations can overflow, the compiler has to generate what is shown on the left. In fact, GC Java by default uses this as required by the Java language specification. So you can see why the difference is.
So what does the C spec then actually say about this particular pattern of multiplying and dividing?
C actually is going to assume that integer operations doesn't overflow.
Oh,
yeah. Now that we have looked at the definition of undefined behavior and how we can detect, now let's look at how we can detect these undefined behaviors, because that's very important. The compiler can issue a warning at compile time when it can statically detect some kind of wrongdoing. So if, based on static analysis, if we can detect that you are invoking undefined behavior, most often GCC would flag a warning. But not all the undefined behavior can be detected at compile time, because some of the inputs might be coming from various other modules. So in those cases, UBSAN or undefined behavior sanitizer can help. GCC gained support for UBSAN from version 4.9, so if you're using 4.9 or later, you can use undefined behavior sanitizer, which is a runtime checker for the C and C++ language. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Okay. Now let's go over some of the most popular undefined behavior-related bugs which we encounter in day-to-day. These were extracted mostly from the bug databases, so I have put the reference to where I have actually got these things, so if you're interested, you can have a look. So the things I'm going to cover here are signed integer overflow, shifting an n-bit integer by n or more bits, divide by 0, dereferencing a null pointer, pointer arithmetic that wraps, and 2 pointers of a different types that aliases, reading an uninitialized variable. So all of these are undefined behavior. Yes, Maximo.
Kugan, are there going to be slides on individual types of behavior later?
Yes, yes. Okay. So let's start from the first. Okay. Here, we have a function foo, which takes an integer as an argument. It's a very simplified test case. And we are adding integer constant 100 to it to see whether the value actually overflows. If overflows, and then the value is going to be less than a. So basically, a plus 100 greater than a is actually checking to see whether the operation actually overflows. And we are invoking this function foo with two values. The first one is 100, a small number which wouldn't overflow. The second one is the integer max, which of course would overflow.
So who has an answer to this question? You have about 30 seconds.
Yeah, that's a possible answer, yep. It's an undefined behavior. Anything can happen.
So if it doesn't have to consider the case where it will overflow. Oh, you mean the result of the actual arithmetic? Oh, yeah, I was saying is just it will just print the same, will take the same branch for both invocations, but what the arithmetic actually produces.
I think what I'm trying to say here is that it depends, because it's undefined behavior, right? So, like, as you just asked, like, integer operation that overflow is undefined. So compiler can assume that the operation doesn't overflow. So that's exactly what's happening. Like, if you compile this program with -0, you would get what the user wanted. Whereas if you compile with -02, the GCC would assume that the integer operation doesn't overflow. So the if condition is always going to be true, and it will optimize away the else part. Again, it's based on the C and C++ language standard, where overflow of signed value is an undefined behavior. And if you don't want to have this behavior, you can in fact tell compiler not to do by giving fno strict overflow or frapv option. And the best way to detect this kind of errors is by using w strict overflow flag to the compiler. And if you compile the test case we just looked at with w strict overflow, the compiler will give you a warning that it is optimizing based on the assumption. And also, if you use fsanitize equal to undefined and run it, you will get a runtime error saying that there is an overflow. The signed integer overflow can implication on security-related applications. It's because defense against most of the software security problem is actually validating your input. If the code you are using to validate your input is having undefined behavior, then the compiler can optimize that part away without you realizing it. And even though you have coded some guard against possible bad inputs, if the compiler optimizes it away, the user, the person who wants to exploit your application can still do that. And a good example for this is buffer overflow. So when you're accessing a buffer, you want to make sure that the index of your access doesn't go beyond the buffer, and also you want to make sure that it doesn't overflow and goes below the start of your buffer. And a lot of the applications actually used to rely on integer overflow for this check, like what is shown on the top right-hand corner. But as we just looked at, compiler can remove that check based on the assumptions that your operations won't overflow. If that's the case, your application will be vulnerable. The worst thing is some of these overflow checks are used as a common idioms to prevent buffer overflow in security-sensitive codes.
So in this particular example, this is caused by the fact that len is a signed type, right?
Yes, it is a signed type.
Assuming that buffer is a pointer, does that mean that a pointer, so that the promotion that happens results in a signed type for the sum of the two?
Sorry, I don't get you.
So buffer, the type of buffer plus len, that's a signed type then?
Yes. Len is the index. We are kind of the index. I mean length.
Len should always be of type size t.
Yeah. Yeah, but yeah. If it is an unsigned, then it's this problem won't happen. But I'm talking about signed type here.
Yeah, I understand. But if you, so that means that in the expression below that a pointer type plus a signed type combines into a signed type. Yeah, it's a pointer.
So yeah,
Is a pointer signed?
Yep. We are doing for point arithmetics here. But what we are trying to, what I'm trying to say here is if the len is negative by overflowing, in that case, buffer plus len less than buffer is possible. But the compiler is going to assume that that won't happen. This particular example is actually taken from the LWN article.
So I guess the question is, we all understand what is the signed overflow when the resulting type is an integer. If buffer is a pointer, what will be the type of buffer plus signed integer? It will still be a pointer, right? Yeah. So we are getting to the question about whether pointer types overflow. And that's unspecified because pointer is not an arithmetic type.
Yes. Yep.
So is there anything in the standard that actually resolves this question? What happens to pointers on overflow?
Yeah, pointer is actually, I think it's unsigned type, right? If I remember correctly. Sorry? Is signed type?
So this seems to be more an example of pointer overflow rather than
no, but
signed integer overflow.
Yeah, but I think in this test case, I don't know whether it's a buffer is defined as a pointer or is as a defined as an integer. I mean, yeah.
So the original code was trying to detect the pointer overflow. of a malicious length passed in, but the compiler, in this particular case when optimizing, removes the check because of the undefined behavior that we're talking about.
So the comparison it eliminates, it's not a signed comparison. So that's, yeah, okay.
Yeah, basically like the compiler is assuming that buffer plus len less than buffer will be always false. Which is, yeah. Yeah, if you don't want this behavior, you can actually use the fno strict overflow flag, the GCC, and it will preserve the meaning of what the user wanted. Okay, this is another example. Here, the function foo takes two arguments x and y, and what in essence it's trying to do is it's trying to right shift the value in x by 32 bits. But instead of giving 32 straight away as a constant, we are actually passing it through as an argument. I took this test case as it is from a GCC bug report. The reason why it's done in this way is actually like to make statically not detectable. And if you compile this program with minus O0, you would get a value 1000 as an answer. And with minus O2, you will get as a 0. Again, shifting an n-bit integer by no bit is an undefined behavior. And if you use fsanitize equal to undefined, you will get a runtime error from the UBSAN saying that you are invoking that undefined behavior. There's also one more interesting example from Chromium, which also was based on the same undefined behavior. And it was actually a simple change, introduced undefined behavior that completely eliminated one of the important security features. Like if you're interested, please look at the link. So this is another example. Here, the test div is trying to do basically divide I by k, but before it does that one, it's checking whether k is 0, and if k is 0, it's trying to be nice by printing that found divided by 0.
So what will be the output?
Yep.
That's the classic case that when he assumes that if k is 0, he already tests for k is 0, so k cannot be 0, so he just removes the test and prints k.
Yep. Yeah, that's exactly what was happening.
For future questions, compiler engineers, please wait, please give others a chance.
Yeah, this was actually from PostgreSQL 8.15, an old one. As Renato just said, compiler assumes that since we are doing I by k, k cannot be 0, and it optimizes away the condition and the print statement. There's also a famous example from Linux kernel, where they were trying to see whether m size is 0, and if m size is 0, they wanted to provoke a signal. But again, since you are dividing by dividing, the compiler assumed that m size cannot be 0 and optimized away the whole code. Exactly, yeah.
Yeah. So
that's one of the reasons why it's made undefined by the standard.
the takeaway point is that even if that compiler can look what is downstream in the program and can extract information from the paths to optimize previous statements based on the subsequent statements. So if it sees something in the subsequent statement, it can extract information and pull it up the execution path.
Yeah, this is another example.
So that implies that undefined behavior could be, there's no chronology in that. It means that the program that has undefined behavior could have it at any point in the execution, even before it ever reaches a point where the undefined behavior is actually used.
Yes, so like if you have a main function and at the end of the main function you have return something defined by 0, it's allowable for a compiler to print out happy kittens to standard output. If there is undefined behavior on the execution path that is to be taken for sure, compiler can do whatever it wants.
The other point is the visibility of the compiler increases with the optimization level. So you may think that the optimization level is buggy, but it's not. It's really the undefined behavior is actually exposed by the higher optimization level because it is able to see more.
If you're interested in that one, there's a blog post by Chris Latner in the LLVM blog that has a case where the optimization of one line of code generates undefined behavior on the next line, and then the undefined behavior on the next line generates undefined behavior on the previous line, and then you optimize the whole function. And that's only because the optimizer is passing through, and then it's just seeing more and more and more, and suddenly says, you know what, you're not doing anything useful, just return 0. Exactly.
Yep. This is another.
Follow up the C standard.
Yeah, this is another example extracted from GCC bug database. So basically, like, this piece of code was trying to see whether the point arithmetics is that wraps. But this is an undefined behavior, and the compiler can again assume that this doesn't happen. And when you compile this code with -O2, it will assume that the condition is always false and optimize the whole thing away and prints no wraps irrespective of what the value is.
Who understands why this is happening? Why the compiler, what is the undefined behavior here? So pointer arithmetic is...
wraps, it's an unsigned type.
And it is undefined.
Isn't pointer arithmetic undefined itself?
No.
That was a question, not... Is pointer arithmetic itself undefined?
I don't think the normal point arithmetic is undefined. But if it wraps, yeah.
Okay.
Yeah.
Essentially, that means that you can never get to a 0 pointer from non-zero pointer, right?
Yep. Oh, yeah. Aliasing different pointers of type. Yeah, that is undefined, yeah.
Yes. Should I repeat? Yes. Okay. It's pointers of different types. A comparison between pointers of different types or arithmetic between pointers of different types is undefined, even though they are pointers and they point to an address in memory, which is essentially almost the same thing, but because the size may be different, then you get undefined behavior.
Yeah. One thing to note here is that current UBSAN doesn't model this behavior and won't give you a warning or error. And So please keep in mind that not all the undefined behaviors are modeled in UBSAN, though it's getting better and better.
Is it possible that there is undefined code in compiler code itself which compiles into another weird, even weirder undefined behavior compiler?
That means it's a compiler bug. Yeah. Yeah. Again, dereferencing a null pointer is an undefined behavior. This piece of code came from Linux kernel, where you get a struct pointer ton, and there was a check to see whether ton is null, and if it is null, they return error. But during refactoring, a piece of code was added which was actually dereferencing the pointer. And obviously this would crash, and what made this worse is compiler optimized away the check, making the subsequent code executable. So it was, I mean, people came up with a working exploit using this. So mapping code to address 0 and making it execute. Again, this is a very recent example of calling a null object from Chromium V8 garbage collector. So here in the while loop, you have an object, and the code is checking whether the object is valid by checking whether this pointer is actually null. But since you are calling a method of that object, the compiler assumes that this pointer cannot be null and returns true all the time. So it makes, this actually causes the V8 garbage collector to crash when the object is null.
So in this case, this pointer will be null?
Yes.
Is it, well, compiler assumes that this pointer can never be null.
Like if you invoke a method, like if you call a method of an object, then this pointer cannot be null.
Yeah.
And the last example is from LLVM. Reading an uninitialized variable is an undefined behavior. So in this piece of code, someone was trying to create a random value using an uninitialized and relying on the data on an uninitialized variable. So compiler can actually assign any value to the uninitialized variable and express and also to the any expression derived from that uninitialized variable. So when you compile this one with a version of LLVM, everything is optimized away, and srandom is called with some garbage value, and none of the get time of the day and get PID is used, because actually you are using that uninitialized value. So.
By garbage, you mean not something that's build time. So not a build time constant, something.
Yeah,
that's
I mean, compiler can even use a constant value all the time.
Okay.
Yeah. So it's not going to be random at all.
So garbage is maybe not.
Oh, okay. Yeah. Yeah. In conclusion, undefined behavior means standard non-conforming code. So compiler will assume that undefined behavior is not present in the code while optimizing. So undefined behavior can be subtle and not always obvious, as we looked at from some of the examples. And the best way to detect undefined behavior is to use compiler warnings, enable all the compiler warnings, and audit the output especially when you move from one version of the compiler to the other. Because like compilers are always introducing new optimizations that can actually expose more undefined behavior in your application. And also know the compiler flag, if any, to disable optimizations that might be relying on undefined behaviors, especially if you are using an existing code or a code written by somebody else that has undefined behavior, which you can't fix it. Thank you.
So we still have several more minutes, and first of all, any questions in the audience?
So do you know if there's a plan to have non-fatal errors in UBSAN, in the sense that currently UBSAN, if it finds an error, it aborts the program, right?
Yep.
So the reason I ask is
Okay.
sometime down the line we want to be able to build glibc with UBSAN and just push it into, say, Fedora Rawhide and have it report errors to us. But then if we do that, and if we expose a bug in, say, system D, then we have an unbootable system.
Yep.
So you want a
Yeah,
way to do that. So
I'm-
is there a roadmap for something like that?
I'm not really sure about, maybe Renato might know that one.
So as far as I know, there is no plans to have any of the sanitizers not be fatal, because this being fatal is a lot easier. So when you have a program say exit now, it's a lot easier than report this somewhere and continue from a known state. It's like trying to debug GDB when the underlying application has crashed and now you're in random memory. So I don't think this will ever happen. Now you need to find a way to, because you're in an unknown state. You have abused of undefined behavior, and the UBSAN detected that you've done something wrong, and now you can't guarantee anything is valid or true anymore. So it makes no sense to continue executing on a state that you have no idea what it is. Yeah, so I understand your predicament, because now you can't see the error message because it's during boot process. Now, could you run this on like a simulator, QEMU or something, and then QEMU will help you see the message?
Unfortunately, that relies on complete coverage of all applications to work. And that's essentially the glibc problem. It's a hard problem.
Any efforts to do this UBSAN stuff in the kernel? Anybody know? I take that as a no.
Any kernel people in the audience?
No, I was just going to say I had people ask for it, but I don't have any immediate plans.
So far in the kernel, we know that there is address sanitizer, KSAN project that does address sanitizer. I don't know enough about the UBSAN internals to conclusively tell whether it is possible to implement undefined behavior checker. I would assume probably possible.
I would assume it's slightly difficult because it's a user-land library as it exists today. So you may have to do some porting to make the runtime support the kernel.
The LLVM Linux project, they were running, trying to run sanitizers on the kernel. I don't know what the success they had, if they even managed to get it done, but they were trying to. So some infrastructure might be done already to get it compiling and running, but I'm not sure he reported anything useful.
Yeah, so to answer Raman's comment about sanitizer being a user space library, for the KSAN, for kernel address sanitizer, it was compiled into the kernel, as part of the kernel, as just a static library that kernel used. And kernel had to provide part of the library, but it was not a huge part. Yeah. So definitely some amount of porting needs to be done because the library assumes user space and make it assume kernel space with all its additional requirements on memory addressing. If you have a question, raise a hand.
I'd just like to say, just looking quickly at the kernel tree, but it seems there's support for UBSUN for PowerPC and x86 in the tree.
Yay. Do we want this for ARM and DirectX 64?
So I guess I just wanted to kind of ask some of the LLVM developers if there's any chance they could actually document what their implementation defined behaviors are, what -f-rat-v is supposed to mean, that kind of thing. So if you look at the GCC docs, it will say this is what is impdef, and for instance, they have some stuff about shifting of signed integers, which is impdef, I think, by the C-spec. But GCC will say you can rely on this; it will do this. And if you look at the LLVM documentation, big fat nothing. So if you're to write code that will run on at least 2 of these compilers, then there isn't even anything that says frat-v does the same thing on both. So perhaps we could have some docs, please.
Do you have a comeback, Renato?
You're absolutely right. We try to be as compatible as GCC on the command line flags. So if you say no strict alias or no pointer check, whatever, it does the same thing. But if you don't have the flag, then God knows what happens. The LLVM's position, at least from all the people that have replied to this question before, is it's undefined behavior, shut up. Right, so I agree with you, and I'll go one step further and ask GCC folks about what they think about this. There was a thread in GCC, LLVM, and Linux. It was a very big cross-thread when Linus Torvalds was being Linus Torvalds, and he said, undefined behavior means the standard is crap. Right? And I don't think he's right, but the users always, when they hit by undefined behavior, or after 3 hours of investigating, they realize they've been hit by undefined behavior, they get pissed, and they say, why isn't the compiler doing the right thing? Now, there were some warnings, and we're saying to the users, you know, these warnings are good, and we are telling you when there's undefined behavior, etc., but sometimes you just can't know because it's an optimization issue, it's not a language issue, right? So you can detect this in the AST maybe if the induction range is static or constant or whatever, you can see this, but if it's not, you can't. So my question is this. The middle end is then optimizing and finding these things and say, whoa, I can rely on this undefined behavior, and then I can optimize this thing. What if every time the middle end or the back end took a decision on undefined behavior optimization, it issued like a flag saying, I've done this. And then maybe the front end, because the LLVM has a way to carry back the error message, so the front end prints the middle end error message or warning message. It will be like a -w, show me undefined behavior optimizations. It will be a hidden thing, not turned on by default, and something that just, it is more or less like a sanitizer for the compiler. Would that make sense?
So I would say that in compilers, it's really nice to get to a state when you're compiling a program that you have dealt with all the user inputs, and you see all of the program as it is, and you can just compile it and assume everything is correct. So what you're proposing is essentially assuming throughout the compiler that there are still user inputs to deal with, and when you're doing optimizations, it's much nicer to already assume that front end have dealt with all the warnings, it have dealt with everything it needs to tell to the user, and now we just can focus on generating the code as fast and as we can.
So in LLVM we have this rpass flag, which tells you, give me the decisions that this specific pass is taking to get my code optimized. So for instance, when I work on the vectorizer, I run this rparse equals loop vectorize, and he tells me, the loop vectorizer tells me, oh, I didn't vectorize this loop because I can't understand this induction variable. Oh, this reduction variable doesn't comply with this and that rule, etc. And this is what the pass is telling me. So if all the passes could say the same thing, you say minus r pass undefined behavior, and then whenever a pass knows it's abusing of undefined behavior, it just says, I'm abusing of undefined behavior in this case.
I think GC is trying to do that. It does not always print it out to the user, because then it will be just too many false positives. It would be a huge number of false positives.
A specific rpass flag that only if you really request.
So I actually had a related question to the audience. Why don't you enable all warning flags when you compile your software project? I see a lot of projects that just don't enable warnings, or they ignore warnings, and when you compile them, there is a huge list in your compilation logs for that. Isn't it just too hard? I have several comebacks on this question, so I'll just go in order.
So I think in many cases you'll find that people don't realize that WAL does not in fact enable even a fraction of the possible warnings. A few projects like Grub does manually enable a metric shitload of warnings, but the thing is, as compilers evolve and develop, they add new semantics to new tests for new warnings. So actually, you will need to keep tracking compiler development to make sure that you're actually enabling all of your warnings in your projects. It would be really good to have a -w, no, I really mean all. Yeah. It would be really useful to have that on GCC, because I would use it every day.
Who had the answer here?
Treat warnings as errors, that's it.
Okay. Sorry.
So the problem with treating warnings as errors is you kind of assume that your clients of your application or whatever are using exactly the same compiler that you are, because most of these warnings are coming out of, or many of them are coming out of the optimizer. As the compiler changes, you get new and different warnings and sometimes less warnings because of changes. And at my last company, we actually tried that with the kernel. We were basically looking at we wanted -w error with exceptions, so we ended up parsing the output to have certain error warnings that were allowed. And then every time a new compiler version would come out, somebody would have to go in and figure out which of these errors were real, which of them were actual issues we needed to fix, and that kind of thing. And it's not, I mean, it's not actually non-deterministic, but somehow the warnings sometimes feel that way.
Okay. Any other questions?
Thank you. We know that there is CPU level undefined behavior. Does any of your compiler make assumptions on CPU specific undefined behavior?
So is the question, do compilers have undefined behavior based on the target that has been compiled? To the best of my knowledge,
No.
not really.
They don't.
We try, if the question is more towards undefined behavior as far as the architecture is concerned, we try very hard that the compiler does not produce undefined behavior as per the architecture that we are targeting. We do our best to get warnings from the assembler, which should be treated really as errors. And that's what we do.
Yeah,
I'm assuming that is the question here.
Yeah, I think the language specification considers that one when it defines certain things as undefined behavior. As Peter said, like divide by 0 is undefined behavior because like different architectures does different thing. Some of them will raise an exception, some of them will silently discard. So yeah, so if there are differences from architecture's perspective, then it should come as a undefined behavior in the language specification.
Okay, I don't see any more hands, and we are out of time. Thank you very much, Kugan. Great presentation.